The following video is for physical science with Mrs. Lewis. We're currently on chapter 25 and it's all about Earth's internal processes, and there's actually 4 sections to this chapter. The first one will be discussing the plate tectonics theory, and that is going to be the foundation for everything else that we're going to be learning in this unit. Next, earthquakes, Earth's interior, and volcanoes. The big idea is convection currents inside Earth cause plate motion. Now, fair warning, all year I've been telling you this isn't going to go away. Well, this is something that's not going to go away. Convection currents and how plates move. So just learn it now and it'll be so much easier on you next time. The main idea from section 1 is Earth's surface is made of plates that move slowly and interact among plate boundaries. Earthquakes occur when blocks of rock move along faults, releasing energy. Earth's layers include the inner core, the outer core, the mantle, and the crust. Volcanoes form when molten rock rises from deep within Earth and erupts from a crack in the crust. Here are some essential questions. If you choose to write it down in your regular notebook versus on the note packet, remember, you do not have to write this down. It is simply a choice. Here are your review and vocabulary words, and as you can see, there's quite a new ones. These new ones, mid-ocean ridge, there's going to be a lot of situational questions on your test relating to all of these. So you need to not only know the definition, but you need to also be able to apply it in many different ways. And here's your new vocabulary continued, so start now. So there was this guy, his name was Alfred Wegener, and he observed that the eastern coastline of South America with western coastlines of Africa, and he noticed that they fit together. Wegener argued that you could match rock types, fossils, mountain ranges, and rock types. And if you found similar formations and structures on each continent, then the continents could have at one time been connected. And so, of course, this was his question or his hypothesis. So talking about continental drift for a minute. So large land animals provide better evidence because they could not have crossed oceans. For example, they're not whales, they're not amphibious. They need land in order to move. So how did it get from South America to Africa? In some cases, mountain ranges located on opposite sides of the ocean are similar structure, rock type, and age, suggesting that they were part of a continuous range. When Pangaea broke apart, the mountain ranges became separated.
Talk about the ultimate breakup. Europe and Africa have been splitting apart from the American continents for millions of years. At a rate of approximately 2.5 centimeters per year, the continents are moving about as fast as our fingernails grow, and as they continue to split, the rift between them, otherwise known as the Atlantic Ocean, will get even wider. And all this drama is leaving behind a major scar, an underwater valley called the Mid-Atlantic Ridge, which tears more and more as the continents slowly move apart. Looking back on the continental relationship puts us a mere 300 million years ago, when Africa, Europe, the Americas, and all the other continents were one big landmass, the famed supercontinent, Pangaea. Due to the constant churning of magma underneath the Earth's crust, they all split up and moved to their modern-day positions. But if destiny in the form of magma and tectonic plates has anything to say about it, the continents might have a chance of getting back together. But how will these stubborn continents kiss and make up? Scientists believe the plates will shift, causing the continents to rearrange and get back together. But in true tectonic plate style, it'll take about 250 million years.
If you're interested, you can go onto your online textbook to Chapter 25, Section 1, and under Lab Manager, there is an online lab that you can do on your computer or on your phone. And as we've learned this year, science wouldn't be science without what? A controversy. Wegener's hypothesis was not accepted by his contemporaries because he was unable to explain the why, a force or mechanism that could drive continents apart. It was not until after Wegener's death that new discoveries on the seafloor helped to support his hypothesis. So that brings us from Pangaea hypothesis to seafloor spreading hypothesis. Those are two different things, and you'll need to know the difference between the two. Harry Hess used sonar intended to detect submarines to develop three-dimensional maps of the sea floor and to make accurate maps of that floor. Hess discovered the Mid-Ocean Ridge System, or MOR, a continuous mountain range on the seafloor and wrapped around Earth. Hess proposed a hypothesis of seafloor spreading, or divergence, to divert, to move away from. Magma from the mantle is forced upward because of its low density. This causes the oceanic crust to crack or fault and then move apart. The faulting causes twin mountain ranges with a long and narrow depression called a rift valley in between them.
Many things going on in this concept of seafloor spreading that it's hard to understand in just one instruction. So I hope that you plan to watch this video a few times, particularly because you do need to be able to explain this process of seafloor spreading in great detail for one of your essay questions on the next test. Let's take a look at this picture. This is an image that if you are able to look at this image and explain the process of seafloor spreading to a parent, for example, you should be able to explain it to me in essay form on the test. So that should be your goal. Here you see the mid-ocean ridge, and this is where, from the mantle, molten material rises through this crack in the crust on the ocean floor. It hardens into rock. It pushes the existing rock away on either side of the ridge equally in both directions. So the rock that is right along the ridge is very new rock, very young rock. It is dense, but it's not nearly as dense as the rock further away from the ridge. As this rock is pushed further along the ridge, over approximately 200 million years, depending on the width of the ocean floor, the rock becomes older, further away from the mid-ocean ridge, in this area, for example, and this older rock is colder because it's further away from where it was created here in the mid-ocean ridge. It's also more dense. This rock here, very close to a deep ocean trench, would be the most dense rock that exists on the ocean floor. So this dense oceanic crust may be subducted here at a deep ocean trench. This subduction happens because this crust is incredibly dense and it is older and colder than the rest of the ocean floor. Also, the continental crust here is very much less dense than the oceanic crust that it is on top of. So when this oceanic crust reaches a deep ocean trench, it will be subducted. At this point, it will melt because in this area you have tremendous friction happening right at this border, tremendous friction, very similar to if you rubbed your hands together really quickly, you would experience heat there. That's friction. And heat is created here. It melts this crust right here along the edge. It melts this crust into magma. From there, the magma could go back down into the lower part of the mantle and be recycled and perhaps come right back up through this mid-ocean ridge. That is a convection current, the main force that drives seafloor spreading. The other thing that can happen to this pool of magma that has been melted due to friction between the plates is it could burst through a crack in the continental crust and create a volcano like you see here. So two things that could happen to this magma as it is melted when it is subducted. Now on the other side of our drawing you see,
so as the video just showed, rocks and sediments on the sea floor, you can tell the ages of rocks and how they're measured because continental rocks will always be billions of years old, while seafloor rocks are less than 200 million years of age due to the constant recycling of the magma. The difference in age can only be explained if rocks on the seafloor are continually being formed. Now, part of the seafloor spreading hypothesis is magnetic polarity of rocks. As the seafloor spreads at an MOR, or mid-ocean ridge, lava erupts to form new oceanic crust. When lava cools, iron-rich minerals become oriented within Earth's magnetic field. Earth's surface is made up of separate slabs of ridge rock that move slowly over Earth's mantle. Now, there's three different types of plate boundaries. Let's talk about convergent. Convergent plate boundary is where two plates collide, they come together, and they form this convergent boundary. So when a thick, buoyant continental plate meets a thin and dense oceanic plate, subduction results. So here's the problems I found in the past with students. They're not quite sure what this means, buoyant or dense. So let's just get that out of the way. Buoyant means I'm going to put a boat on the ocean and it's going to float. It's buoyant. Okay. Dense is I can take something the size of a fingernail and it's going to sink in a bowl of water versus a golf ball, or a ping pong ball, which will float on the top. Size doesn't matter. It matters the weight, how dense it is. So if we were to measure this picture and we measured the oceanic crust being 1 inch compared to 5 inches of continental crust, our brain would immediately tell us, well, this is heavier. Well, if you remember the fingernail of gold to the ping pong ball, which one's going to float and which one's going to sink? So in this case, the oceanic crust is more dense. It's going to want to sink. This is going to want to be buoyant, meaning float on top. So this is naturally going to subduct. Your oceanic crust will always 100% of the time subduct underneath continental crust, 100% of the time. So again, subduction is the process where the denser tectonic plate dives beneath the less dense plate along a convergent plate boundary. And the region of collision also has a deep sea trench that parallels the zone. So landforms is also going to be a big part of this entire unit. I'm still talking about convergent plates. They're also known to exist between two oceanic plates, and in this case, the oceanic plate that is colder and therefore denser will subduct. Magma erupted here produces chains of volcanic islands called island arcs. Here's an example of an island arc. It's found in America, and it's called the Aleutian Islands. And a second arch island found in Japan. It's important to note that convergent plate boundaries, as well as many other boundaries, they don't happen just on the ocean or just on the continent. They can happen in many different places. And even though it may be the same motion, it's going to have a different name. So let's take a look at two continental plates. Both have low density and they collide. And they tend not to subduct because they're both buoyant. Why? They have low density. The plates collide and buckle upward to form a high range of folded mountains, and volcanic activity is noticeably absent, and there's no trench. So on to our second plate boundary, divergent. At a mid-ocean ridge, magma rises up between the Rift Valley, which we've already discussed, spreads and cools to form a new oceanic crust. The boundary between the two plates that are moving apart is called a divergent boundary. It diverges or divides from each other. This is the first of 2 videos for 25.1. Please continue on to the second series.